Welcome to the UGC lecture series. This lecture series is the EPG Pathashala lecture series, in which we will be talking about the course on data structures. Up to now we have spoken about basic abstract data types, which is the perspective in which we are doing this course. Along with we covered one particular abstract data type list and one particular implementation of the abstract data type list. In this module, we are going to talk about the linked list implementation of the list ADT. So, that is what we are going to talk about in this module. So, this module also is going to go into detail of the different types of linked lists that are used for implementation of list. Again, as we discussed in the last module, the importance is what are the type of operation that you want to do with that list ADT, that determines the actual implementation. So, what are the objectives of this? Learning objectives of this module are to understand linked list implementation of the list ADT, to explore the singly linked list, circular list and doubly linked list implementation of the list ADT and see the pros and cons of each implementation, to know about the representation of polynomial as a linked list. Here we do a slightly different variation, where we talk about polynomial, how it is represented as a linked list, and talk about the polynomial as an ADT. So, we are not going to use just the normal data structures, we are defining something called a polynomial abstract data type, and what are the operations required for it, how to implement it. Okay. And here we are talking about list, linked list, pointers and the polynomial representation. So, the linked list implementation is nothing, in other words is also called a pointer implementation. So, here the list is not stored contiguously. The main difference between array and linked list is, in arrays the memory locations for that particular implementation of a list using arrays, the elements of the array are stored in contiguous memory locations, while in the linked list representation we do not store the elements contiguously, we use what is called a linked list. It is a series of structures that are not necessarily adjacent in memory. So, compared to the array implementation, the pointer implementation uses only as much space as needed for the elements currently on the list. That means, it is a dynamic representation, where you use only as many elements as needed, but the slight disadvantage, which is not considered very serious, is it requires space to store the pointers. So, in other words, though the elements are of a list, when you store it using linked list, is logically adjacent to each other, physically they are not adjacent to each other. So, lists with linked lists are more complex to code and manage than arrays, but they have some distinct advantages. So, they are they are difficult to actually implement and manage. Dynamic linked list can grow and shrink in size. So, you will use as much nodes, we call them as nodes, where you want to store. So, suppose you have 10 elements in the list, 10 nodes are used, but and if you delete 2 elements, 8 only, those 2 can be returned to a memory. We do not need to know how many nodes will be in the list. Initially, there is no need to decide on this is going to be the maximum size. They are created in memory as and when needed. So, that is one. Easy and fast insertions and deletions. This is the major advantage of using linked list. To insert or delete an element in an array, remember, we have to copy the temporary variables to make room for new elements. We have to close the gap and do shifting. With the linked list, there is no need to move other nodes, only need to reset some pointers. So, here we will reset pointers, will not do any shifting. In arrays we do shifting, in linked list we do not do shifting, we do resetting of some pointers. So, linked implementation requires no estimate of the maximum size of the list. So, there is no wasted space, I do not have to make an estimate. Remember, in array implementation I cannot afford to make too less an estimate, then it will give a maximum size error and come out. If you give too much of overestimation, then you are wasting memory. So, print list and find will take of the order of n, find kth will take the order of n, insert and deletion will take the order of 1. So, if you look here carefully, this type of implementation is more suited when insertion and deletions are very common in your application, and you have chosen a list ADT that where you say that insertion and deletions are the most important operations of that ADT, then you would choose the pointer representation. Insert at any position 0, making a new element. Insert does not require moving of other elements. Similarly, delete at position 0 requires no shifting at all, whether it is at position 0, in the middle, or at the end. Insertion and deletion comes easier, but finding the kth element moves from, you have to move from the beginning of the list to whatever the element is. So, that takes more time. So, if you see the two implementations, for some operations array is better, array implementation of list is better. Still we are talking about the list ADT only, remember that, but the linked list implementation is better when you have to do insertion and deletion operation. So, now let us look more in detail on what is meant by a linked list. So, a linked list is a series of connected nodes this way. Each node contains at least, there are different types of linked list. We are taking the simplest one first. Each node contains at least a piece of data. This could be any type. Here it is an alphabet, it could be a number, it could itself be a record, it can be anything, and a pointer to the next node in the list. So, this pointer gives the address of the next node wherever it is in memory. So, this is there are some linked list implementation which use a header, some which do not. So, here you have a header, this will have a address of the first node, this will contain the address of the second node, and so on. The last node will have a null saying that you have come to the end of the list. So, heads points to the first node, the last node points to null, and note the nodes in the linked list can be spread out anywhere on the memory. So, for example, the address of this node can be 100, this can be 700, this can be 500. I am just telling an example. So, there is no contiguously, they are not next to each other in memory, but logically through the pointer they are next to each other. So, let us look at insertion. You have a linked list, perhaps empty, perhaps not, perhaps ordered, perhaps not. So, you can have all types. You want to add an element into this linked list. Now, you have a head pointing to the first node. The possible cases of insert node are, you want to insert into an empty list, that is possible. You want to insert in the front, that is also possible. I mean, these are the cases. You want to insert at the last node, or you want to insert in the middle. These are the 4 cases that are possible for insertion of into a list. Okay. So, but in fact, we need to handle only 2 cases. Insert as the first node, that is case 1 and case 2 are similar, case 3 and case 4 are similar. So, the actual insertion performs the commands to do the insertion. You have to first create a new node. When you are doing an insertion, remember there are only as much memory allocated to the linked list implementation of list as there are elements. So, when you want to insert an element, you have to create a new node for it, which we in this case we called a free node. Then you add the data to the free node, update the next pointer to the free node, and update current to point to this position, to point to this new node. So, we will look at this. So, suppose you have this is insertion in the front. So, I want to insert 93 to this list. So, what head is initially pointing to this. No, there is no work to find the correct location, because head will always point to the first node. Empty or not, head will point to the right location. So, what I do is I take a free node. Okay, I call the function free node to create a new node. In that new node, I put the new node dot data equal to 93, and new node not next to point to the previous head. I mean, the head was initially pointing to this, that I make, and now I update the head to point to the new node. That is it as far as insertion in front is concerned, no movement, nothing. So, what did we do? We created a new node, made its data equal to 93, made its next is the pointer to point to the previous this address we want to point to. Initially head was pointing to this. So, we make it point to this, and then now the head is has to point to this node containing 93. That is what we did here. Now, insert at the end. Okay. Now, when you are inserting at the end, I want to insert 93 at the end. Again we have second 93. There is need to find the correct location. We need to know the address of the last current node in order to connect to the new last node. So, need iteration. So, this is a common operation that we have, where we want to find the address of a new node, either by looking at the data stored there or at data of the previous node. So, we need a search pointer p, we will call this as p. Initially p will start with head, and you will search until p dot next is null. Okay. So, this is p, this dot next is null. Until that is reached, we will keep we will loop. Okay. So, this is a loop. So, now P points to this. Okay. So, P is equal to P dot next. Now, P is the last node before insertion. Search until P dot next is equal to null. P dot next is equal to null. Now, P is dot equal to, now P is the last node. Free node is equal to new node. New node dot data is equal to 93. New node dot next is equal to null, and this P dot next is equal to new node. P dot link you said is equal to new node. So, inserting after middle of unsorted list and sorted list, recursively transfer until you find the correct place to insert, either after a particular data value or find the correct place in a sorted list. So, you can either give a particular data value. If it is a unsorted list, you can give a particular data value and say I want to insert after that, or if it is a sorted list, automatically the correct place will be found, compared to if you need to insert before P. If adding largest value, then you will have to insert at the end. So, this is an insertion after. So, the use of search through index for array pointer is a common need, as I already told you. So, what we do here is, in this case we are searching for a particular element in the list. So, we want to insert after 17. What do we want to insert? The node 88. So, what we do? We need a search pointer P. Initially we make P point to head, and then you search until P dot next dot data, that is P dot, this you start with P, come here, P dot next, that is this node's data is equal to 17. So, now we need to add a node after a node with address P. Okay. Now, this is a very important point that you have to note, that I cannot directly go and find. I could have said P dot data equal to 17, but then I cannot do insertion. I need to insert after 17. I can't do that, because now what happens? I need to set this pointer properly. So, I need to add a node after a node with address P. So, I create a new node, put its data value as 88, and then I put new node dot next is equal to P dot next dot next, and now the new P dot next, this new P dot next will point to the new node. So, now let us look at insertion into a sorted list, where previously we had just inserted into an unsorted list. Here we have to find the correct position. So, now suppose we want to insert 50. Now, as you know, this has to be inserted here. Okay. We need to start from head using a search variable P until we find the address of the node after which we need to insert. So, I want to find the address of 40. Okay. But now note the point that if I want to find the address, I mean I need to know that I want to insert after 40, I need to know that I have reached 60, which is an area, I mean which is a value greater than 50. So, for this we need to ensure that the node after this has a value greater than 50. So, I will put P equal to head, and then I will loop until P dot next dot data is greater than 50. So, this is P, this is P dot next, and the P dot next is data is 60 or greater than 50. Okay. So, I will keep doing this till I mean this P is equal to P dot next is done to keep on moving through the node. Now, at the end of the loop, P points to the node containing 40, and P dot next dot data contains 60, which is greater than 50. So, now how do we do the insertion? So, what I do now, as I already told you, at the end of the loop, I have this as P and this is P dot next. Okay. Now, I first create a new node, I put its data value equal to 50. Okay. Then I put its next value equal to, has to point to P dot next. So, new node dot next is equal to P dot next, which I set. Okay. Then that is the second step. In the third step, I have to put, now after, okay, P dot, now the new P dot next is no longer this, but is this. So, I have to put P dot next is equal to new node. So, that is what I do here, that is the third step. Okay. So, now what has happened? I have finished the insertion. Now, what you have to note here is very importantly, if you do this step first, that is I put new node 50 and I put P dot next is equal to new node, then I have lost this address. So, I necessarily have to do this before I set p dot next. This is something that you have to note. So, that is why the order in which the pointers are set is very important. Now, let us look at deletion. So, you have to begin with an existing linked list. It could be empty or not empty, could be ordered or not, it could be either way. So, there are 3 main situations. Delete. So, this is the node, and you can delete 40, you can delete 60, whatever. So, there are 3 main situations. You can delete the first node, in which case you have to do some manipulations to head. You can delete the first occurrence of an element. You can delete all occurrences of a particular element. Deletion involves getting to the correct position, moving a pointer, so nothing points to the element to be deleted. So, this is the basic of deletion. I will just explain it once more. First of all, as we did in insertion, we have to find out which is the correct position, okay? And then you have to move the pointers up, so that this nothing points to this new node. So, that new node automatically becomes isolated, in other words. So, that is what you do in deletion. So, let us look at deletion. So, suppose I want to delete 40. So, I am not doing the searching here. So, this is the node q, this is p, this is p dot next. I want to delete p or the 40. So, first thing I do is q dot next, which was pointing to p, should no longer point to p, it should point to p dot next. So, this q dot next should point to p dot next. So, that is the first step we do. Okay. Then now nothing is pointing to this. So, I can remove this node. Okay. So, that is simple. So, what I have done is, this was pointing to this node, actually, okay, I will explain this once more. This, okay. So, this is what we did q dot next is equal to pointing to this. So, that is what we did. Now, actually this pointer we have not made anything, but anyway this is not accessible in the list. So, that can be ignored. So, p now can be a node that can be removed and stored away. Okay. So, that is a simple deletion. Now, linked list this is using singly linked list. Why we call it singly linked list is there is only one pointer variable, it points only to the succeeding node. That is why we call it a singly linked list. That is, the node has a data and a pointer. Now, traversal means visiting or examining each node. This is again an operation that is very commonly used for all data structures. So, in the simple linked list we start at the beginning, go one node at a time until you reach the sum that node dot next is equal to null. So, given a head pointer, you looks at just one node and then if it is like that, that is, you can give a function first then next, and you can do the traversal also. So, what are the advantages of singly linked list? Quick update operations such as insertion deletions at both ends and also at the middle of the list. Now, advantages of, there is something called a doubly linked list, which you will see, which stores 2 references, a next link that points to the next node in the list and a previous link that points to the previous node in the list. Now, this is a quicker updation operation over singly linked list, which we will see as we go along. Now, before we go to doubly linked list, we will see something called circularly linked list. Now, what is the circularly linked? The last node points to the first node in the list. How do we know when we have finished traversing? Check if the pointer of the current node is equal to the head. So, if you have a head pointing to the current node, then you can start from here, but if you have reached this, you will know. So, this is a circularly linked. Can you think of why you need a circularly linked list? You need a circularly linked list because you want to traverse the list and not necessarily check for null. If you have a head node, you can use circularly linked list. This allows you to see from B you can go to C. By traversing the list, you can also reach the node that is previous to A, which is not possible in previous to B, which is not possible in a singly linked list. So, may need to cycle through a list repeatedly. For example, if you are trying to implement the round robin method of a shared resource, you first you know what is a round robin method. In a round robin method, suppose I have 5 people and I have say some number of chocolates, I give 2 to the first person, 2 to the second person, 2 to the third person, 4th person, 5th person, then I take 2 again and give it to the first person. So, the first person will get chocolates every 5th time, like that. That is called round robin. I said chocolates, it can be time allocated and so on. So, in a lot of operating system sharing resources, this type of time round robin method of allocation of resources is fairly common. So, for those type of application, you can make the last node point to the first node. that is, it is not a one time allocation, it is a allocation again and again. So, this is an example as we already saw. Now, doubly linked list, as we just talked about briefly. Doubly linked list, we have two pointers, one pointing to the previous node, that is the predecessor, and one pointing to the next node, that is the successor. So, a doubly linked list has two references, one to pointing to the next element and one to the previous element. This makes moving back and forth easier and eliminates the need. Now, if you have noticed very carefully, in a singly linked implementation of a list, we always needed to know the address of the previous node. Suppose I am searching to delete this node P, I needed to know the address of the previous node. So, normally what we did, we maintained, we went on searching till we found some P dot next had some condition. So, that I get P. P dot next actually is the condition that has to be, I mean the node that satisfies the condition, but I also have P, the address of the previous node. So, unless I do this, I could not do insertion or deletion. So, that eliminates the need of a previous reference that we saw in the previous algorithms. Disadvantage, you have obviously a bit more overhead because you have two pointers instead of one. So, a doubly linked list provides a natural implementation for the list ADT. We are still in list ADT. In list ADT, in the previous module we covered array, vector and dynamic array implementation of the lists. Here we looked at singly linked list implementation, circularly linked list implementation, and now we are looking at the doubly linked implementation of the list. Nodes implement position and store data. So, here you have data and you have link to the previous node and link to the next node. Special trailer and header nodes also you can have. So, to simplify programming, normally these header and tailor nodes are called sentinel nodes. So, you can do implementation with the sentinel nodes, where you will be just using two extra nodes to keep track of things. So, those they are called as sentinel nodes. Head and tail nodes, they are dummy nodes called sentinels that do not store any data elements. Header sentinel has a null previous pointer, it will have only one next pointer pointing to the first node, and trailer sentinel has a null next pointer, it will have a previous pointer pointing to the actual node, while it will have a null next reference. So, a doubly linked list object would need the following, store the following: the reference to sentinel head node, reference to sentinel tail node, and size counter that keeps track of the number of nodes in the list. So, when you count the number of nodes, you do not count the two sentinels. So, this is an empty linked list which has the two sentinels. Using 10 sentinels, we have no null links. Instead, we have head dot next is equal to head dot next is equal to trail, and trail dot previous is equal to head. Now, this is a node with a single node. I mean, this is a doubly linked list with a single node in the list. So, this single node is the first node. It is also the last node. So, the first node is header dot next, okay, and last node is the trailer dot previous. Now, let us look at insertion into a doubly linked list. Again, possible cases are at the front of the doubly linked list, at after a given particular node, and at the end of a doubly linked list. So, let us look at the insertion in front of a doubly linked list. So, as usual for any insertion, you have to find a new node. This new node should have the structure of having place to store one data and two pointers, the next and previous. So, this is a new node. So, let us assume that I want to insert 10. So, new node dot data is 10, okay. Then we want to insert at the front. So, the second step is new node dot next is equal to head dot next, okay. Then head dot next is head that next, because we had previously told you in the previous singly linked list we assume that head is just a pointer. Here we are assuming head is a node which has previous is not defined, you have head dot next pointing to the first node. So, new node dot next is equal to head dot next, and new node dot previous is equal to head itself. Then, so now the fourth step is head dot next dot head dot next dot previous, that is this node's previous should point to new node, and head dot next should point to new node. Now, here if you look at the way in which the pointers are set is very important. So, what we did, I will just repeat this first one alone, I will repeat again. So, you have a new node. Please note, you must remember that here we are assuming that the head node itself, here the head node itself has got that next, which will point to the first node. So, what we have, a new node in which you put the data point. So, that is done. Then new node dot next, okay, will point to head dot next, that is what we have here, head dot next. Then we have new node dot previous will point to head, that is also fine. Now, this node previous has to point to new node. So, what is that node? Head dot next, that is this head dot next dot previous. So, that is what we are doing, head dot next dot previous will point to new node, and then the next thing is this head dot next has to point to this. So, head dot next is pointing to the new node. So, these two implementations have been removed and replaced by these. Now, if you want to insert after a given node, so now insert after 20, you need an iteration, we need a search pointer. Initially p is equal to p dot next, and you will search until p dot next data is equal to 20. Now, we need to add a node after the node with address. So, at the end of the loop p points to the node containing data, because p dot next dot data contains 20. Okay. So, new node is 30. So, new node dot previous is equal to p, new node dot next is new node dot next is p dot next, and then so we want to add after this. So, now next is p dot next dot previous, that is p dot next dot previous is new node, and then p dot, this can be done, this has to be done before the next step. What is the next step? P dot next is equal to new node. Okay. So, these two has to be done in this particular order, which I already told you before. This is at the end of the loop. Okay. I mean, so this is at the end after a given node. Now, at the end of the loop, you have a new node. I am not going too much in detail. You put 60 there. New node dot next is equal to tail. Then new node dot previous is equal to tail dot previous. So, you can't set tail first. You have to get this node and then make it new node dot previous point to tail dot previous. Then you have tail dot previous dot next pointing to the new node, and then you have new node pointing to tail dot previous dot previous pointing to this tail dot previous pointing to new node. So, this is the order in which you will have to do this. So, similarly, you can delete a node from a doubly linked list. Again here this is the element p, this is the p, and this is t is equal to p dot data. This is p dot previous, this is p dot next. If you understand and keep it this way, it is much easier to understand. So, now p dot, so first thing is p dot next dot previous, this is p dot next address, that previous has to point to p dot previous. So, this element, then p dot previous is equal to this, now points to p dot next, this node is no longer there. So, that is pointing. Then I am making p dot previous null, p dot next also equal to null. Okay. So, that is it, and now you have finished the deletion. So, and then you can remove the node p. Now, in the implementation of the list ADT by means of a doubly linked list, the space used by a list with n elements is n, but the idea is that it runs with a operations of insertion and deletion take almost limited time. Advantage is you can access any element as long as the external link to the first item is maintained. Insertion of new item does not need any shifting, that is the important part. So, if your list ADT has a number of insertion deletion, this is the best implementation. Deleting also does not require any shifting, and you can expand and contract as necessary, as we already told, because you use as many nodes as needed only. So, disadvantage is obviously the overhead of links, you need 2 extra links, and dynamic means you need to construct a new node and delete a new node, and you do not have direct access to any element using an index, you have to go from the beginning. So, that is the major disadvantage. You have to go through the first element, second element, and that iteration is necessary. Now, we will just look at a polynomial ADT, as I already explained in the beginning. So, this is an example of a single variable polynomial which you would have seen in your school days. The order of this polynomial is 6 because the highest power is 6. So, why would we call it an abstract data type? Because you can generalize like this and represent it like this. So, there are two variables, one is the coefficient of the object and the other is the exponent. This can be a real number while this is only an integer. So, by definition a set of values and set of allowable operations. So, what are the operations you would allow on the polynomial? Addition and subtraction, multiplication, differentiation, integration, this is possible. So, this is just to tell you that an ADT need not necessarily be only a conventional data structure, it can also be a polynomial where you represent the polynomial and the operations of the implement the operations of the polynomial. So, in both array and linked implementation, many operations are similar in efficiency, but most are 0 1 except when shifting or searching is needed, in which case they are of the order n, in searching for linked list implementation and insertion and deletion in the case of array implementation. In particular situation, the frequency of the need for particular operations which I have been telling you may guide the use of one implementation over the other. So, in this we discuss the implementation of list ADT using linked list. We explain the different types of linked list, singly linked list, doubly linked list and circularly linked list, and we outlined something called a polynomial ADT, which means ADT can be defined even with complex objects. Thank you.